The purpose of this video will demonstrate to the viewer the principles of this new innovative device. To facilitate this, let us first review the generic form of a refrigeration cycle of an air conditioner. The standard air conditioning system is composed of four primary components. These are the compressor, the condenser, the expansion valve, and the evaporator. The refrigerant enters the compressor as a low-pressure, low-temperature gas. The compressor does work on the refrigerant, transforming it into a high-temperature, high-pressure gas. The refrigerant is then pumped into the condensing component of the air conditioning system, where it is transformed from a gas to a liquid or gaseous liquid state. The gaseous liquid form is defined as a state of the refrigerant that is somewhere between a gas and a liquid. This is accomplished by passing a cool ambient airstream across the coils, which transfers heat from the refrigerant to the airstream. The refrigerant is then passed through the thermal expansion valve, where it is flashed into a gaseous liquid form, which causes the temperature and pressure to drop dramatically. The very cold refrigerant is then passed through the evaporative coil, where it is transformed from a gaseous liquid state to a gas state. This process is facilitated by a hot air stream, which is drawn across the coils of the evaporator, increasing the temperature and pressure of the refrigerant by transferring heat from the airstream to the refrigerant. It is known that a refrigeration cycle is adversely affected when subjected to elevated ambient temperatures at the system condenser. When the cooling demand is held constant at the evaporator and the condensing ambient temperatures are allowed to fluctuate between a low of 45 to a high exceeding 100 degrees, the system experiences an increased energy consumption at or exceeding 30%. The AC Companion innovator has engineered a means by which an artificial environment is established during the system's condensing phase, hence allowing the system refrigeration cycle to perform at its maximum efficiency while subjected to a less than optimum ambient temperature conditions at its condensing coil. The AC Companion consists of two independent refrigeration circuits in conjunction with two mutually exclusive hydronic loops. The primary stage AC Companion stabilization loop incorporates an AC Companion heat exchanger downstream of the condenser coil. The secondary stage AC Companion charging loop incorporates an AC Companion heat exchanger in substitution for the primary evaporator of the AC Companion stabilizing loop. The refrigeration loops are isolated from one another, operating independently through interconnected refrigerant valves controlled by the System Logic command module. Both heat exchangers, acting independently, are served by the hydronic loops sharing a common glycol pump and an ice storage vessel. These loops are activated through a set of three-way valves operating in conjunction with a controlled glycol volume at the heat exchangers and loop selection through the instrumentation and a time clock contained within the system control module. The AC Companion stabilization loop is engaged upon demand for refrigeration, when space cooling and ambient temperatures are near their peaks, typically between the hours of noon and early evening. The AC Companion charging loop facilitates the operation of the AC Companion stabilizing loop by charging the ice storage vessel. It operates when the ambient temperatures are near their lowest point, typically late at night or early morning hours. The AC Companion stabilizing loop and the AC Companion charging loop are not permitted to run simultaneously. Primary stage AC Companion stabilizing loop. The AC companion stabilizing loop contains the primary components that contribute to the enhancement of the standard refrigeration cycle efficiency and is operational when there is a demand for cooling. The innovator augments and improves the efficiency of the refrigeration cycle found in a standard air conditioning system by the introduction of a heat exchanger downstream of the air conditioning condenser. The heat exchanger is defined by an interface between a glycol solution and the system refrigerant. Heat is transferred from the hot refrigerant to the low temperature glycol solution, thus reducing the overall temperature of the refrigerant significantly. The refrigerant exits the heat exchanger and continues through the remaining components as found in the standard refrigeration cycle, as shown in the first segment. The glycol heat transfer medium is then routed to the ice storage vessel. The ice storage vessel is defined as a heat exchanger with an ice-glycol interface. The glycol heat transfer medium is dynamic, whereas the water solution is the stagnant component of the storage vessel. The glycol thereby transfers heat to the solid ice solution, resulting in a phase change. The glycol then leaves the ice storage vessel at a significantly reduced temperature and continues its path through a series of hydronic control valves. The valves function to provide both volume control and loop selection. Exiting the valves, which are managed by the System Logic Control Center, the glycol re-enters the AC companion heat exchanger. The aforementioned process simulates an artificial environment at the condensing coil found in the standard AC refrigeration cycle, consistent with an ambient temperature of approximately 60 degrees. This allows the air conditioner to always perform at its optimum efficiency. Secondary stage AC companion charging loop. The secondary stage AC companion charging loop facilitates the function of the primary AC companion stabilizing loop. The AC companion charging loop contains the secondary components that contribute to ice formation at the ice storage vessel. This is facilitated by substituting an AC companion heat exchanger in parallel to the standard air conditioning evaporative coil. The air conditioning evaporative coil is isolated or taken out of service from the refrigerant loop of the AC companion charging loop by employing two refrigeration isolation valves. The heat exchanger is defined by a refrigerant glycol interface, whereby heat is transferred from the glycol solution to the refrigerant. The refrigerant exits the heat exchanger at an elevated temperature and continues through the remaining components of the AC companion stabilizing loop. The glycol heat transfer medium exits the heat exchanger at a temperature conducive to ice formation at the ice storage vessel. The glycol, at an elevated temperature, exits the ice storage vessel and is routed through a series of hydronic control valves managed by the System Logic controller. The valves function to provide both volume control and loop selection. Exiting the valves, the glycol re-enters the AC companion heat exchanger, whereupon the charging process is repeated. The System Logic controller monitors and controls the AC companion charging loop to ensure a complete phase change within the ice storage vessel, whereby the system is shut down in preparation for the following AC companion stabilizing loop function.